We've all noticed stars twinkle in the night sky. This occurs naturally because starlight travels through moving air. This video will focus on active optics, a set of technologies used in modern telescopes to minimize the imperfections in an image due to atmospheric turbulence. As previously mentioned, stars twinkle due to light traveling through moving air. Refraction occurs because there are slight variations in density and temperature between different pockets of moving air. Astronomers often refer to this seeing on a given evening by describing how much twinkling is occurring due to atmospheric effects and the present quality of observing. We can illustrate a related phenomenon with the apparatus shown here. We turn on the laser and aim it directly at a target placed on the wall. Note that our laser spot is intense, steady, and focused. We have a heating plate to turn on underneath the laser light. Let's explore this with a pure instruction question. What will happen to the laser spot when the heating plate warms up? Classroom students should follow normal procedures or instructor guidelines. Viewers not in a classroom should record your vote and explain your reasoning on a piece of paper. Please pause this video and answer the question. Note that the laser spot is at a slightly different location. This is due to refraction, as the light bends as it enters and leaves the warmer, lower density air. Note that the spot dances around as well. This is due to convection currents in the air carrying away heat energy from the hot plate. We can see something similar by looking at this animation of a fire pit. As the animation progresses, we can zoom in and see the convection currents causing air turbulence as labeled. Most modern large telescopes go farther by employing active optics, actively shaping the telescope's mirror to minimize the negative effects on images due to temperature, wind, and mechanical stress on the mirror. The first fully active telescope was the European Southern Observatory's 3.5-meter New Technology Telescope, which began operating in Chile in 1989. The temperature and airflow around its mirror are precisely controlled. The New Technology Telescope's thin mirror is actively shaped during observations by computer-controlled actuators that provide varying forces. The actuators get input from an image quality detector and keep the mirror in its optimal shape. All large telescopes make use of active optics today. A related technology is adaptive optics, deformations of the mirror over a much shorter time scale to minimize the effects of atmospheric turbulence. In this image, you can see a laser mounted on the telescope exciting sodium atoms in the upper atmosphere, which creates an artificial star whose properties are well known in the image. Adaptive optics then corrects for the effects of atmospheric turbulence on this artificial star and other objects in the field of view. Adaptive optics techniques are also very common in large telescopes today. More teaching materials can be found online at astro.unl.edu.